Okay, let's start with a new recurrence relation, which is T of n equal to T of n minus 1 plus n. So what this indicates that we have a problem of size n. This problem of size n is divided to problem of size n minus 1 at each recursion step or each iteration, and to divide this problem of size n to n minus 1 we need locally computed time to be n. So what does this mean? This could be one case could be we have an array of size n, and each iteration we are reducing that array to n minus 1 size, and to do that we need to traverse over the entire array of size n, right? So that is why this could be one of the possible case of that. So now how we can solve it? So let's take we have a problem of size n, T of n equal to T of n minus 1 plus n. Okay, so now let's start n is replaced by n minus 1. So n is replaced by n minus 1, so our equation will become T of n minus 1, which is equal to T of n minus 2 plus n is replaced by n minus 1. Now if I replace again n by n minus 1, it will become T of n minus 2 equal to T of n minus 3 plus n minus 2. Now again if I go further, T of n minus 3 will become T of n minus 4 plus n minus 3. So if I go on further till I'll just go to one step, that step I could say T of n minus k equal to, so you can see that if I make this term as a k, what is this term? K plus 1, right? So that is why T of n minus k plus 1 plus n minus k. You can see that this 3 and this 3 is same, but this is k plus 1 term. So now this is the kth term of the series, and k minus 1th term could be now T of n minus k minus 1 equal to now T of n minus k plus n minus k plus 1. If you remember, this is n minus k plus 1. So now let's try to put these values in our original equation and check how it will behave. So we have T of n, which is equal to T of n minus 1 plus n. Now replace T of n minus 1 by whatever value we have here is n minus 2 plus n minus 1. So now I will be getting T of n equal to T of n minus 2 plus n minus 1 plus n. So now this entire term is T of n minus 1. Now this T of n minus 2 I have to replace with the T of n minus 2 we got here. So I'll go here now, T of n minus 3 plus n minus 2. So this is for T of n minus 2, and what are the remaining term before in previous step? That is n minus 1 plus n. So this term will become T of n minus 2. So now if I go further, T of n minus 4 plus n minus 3 plus n minus 2 plus n minus 1 plus n. And now what is this term? That is T of n minus 3. So now let's write a kth term or k minus 1th term in the series. First we'll write or directly I'll write kth term. So now I'll be getting T of n minus k. So if I get T of n minus k here, if I get T of n minus k here, what could be the next term? If I could get t of n minus k here, you can see that this is t of n minus k, and what will be the term? Next term will be n minus k plus 1, and that is like this bracket will be there. If you remember, if you look here, this is n minus k, so this term is k now. So what could be this term? K plus 1, right? This is 4 and this is 4 minus 1, sorry, so it should be k minus 1. So now our term will become n minus k, and this is n minus k minus 1. The next term will be k minus 2, right? So plus n minus k minus 2 plus so on terms till n minus 1 and n. So just see this step, like whatever we have done, this is n minus 4, and now if I make 4 as a k, so this term which we have here, like let me, yeah, so this term which we have here is 4 minus 1, right? So 4 here, and this is 4 minus 1. This is this next term is 4 minus 2. So same way I have t of n minus k in this case. So now I have plus n minus k minus 1, that is this one. So now if I expand this, my t of n will look like this. T of n, which is equal to, I have now t of n minus k plus, now if I expand, or if I just multiply minus n to this bracket, it will become n minus k plus 1 plus n minus k plus 2 plus n minus k plus 3 plus so on term till n minus 1 plus n. Now what is our aim? T of 1. So now if I have t of 1, I need to find out, like, and what could be the case? Like it could be a constant c, or let's assume it 1. I'll tell you why I'm choosing 1. T of 1 equal to 1 I will choose for simplicity now, but I will show you like even we'll just go with c also. So now n minus k is equal to now 1 I am making. So now, so that I can get t of 1. So now what I will be getting? N minus k equal to 1. So I should get k equal to, no need to have k equal to n minus 1. But we already know n minus k equal to 1. So now if you just see the equation for t of n, what we will be getting? So t of n equal to, n minus k is 1, so I will be getting t of 1. Plus n minus k is 1, so 1 plus 1, 2. So he can see n minus k is 1, so 1 plus 1, 2. This is n minus k is 1, 1 plus 2, 3. So plus 3. N minus k is 1, 1 plus 3 is 4. So plus 4, and so on till I will go to n minus 1 plus n. Now if I choose t of 1 equal to 1, why I am just saying t of 1 equal to 1 I will choose, so that I will get 1, 2, 3, 4, so on till n minus 1 plus n. So this series is sum of first n natural numbers. So what is the answer for sum of first n natural number? N into n plus 1 divided by 2, or I can also write 1 by 2 into n square plus n. So by looking at this, the complexity will be big O of n square. So for this problem we got big O of n square as our complexity. What is the case if I have t of 1 equal to c? It won't be changing much, the complexity will remain same. C, instead of 1 I will having c as a constant, plus 2 plus 3, like it is c plus 2, right? C plus 2, c plus 3, and so on. Anyway you are summing till n. So this is also one series, like it will be like n minus k c, then you got c plus 1, then you got c plus 2, then you get c plus 3, so on, and you will sum till n number. So this will also be one of the series which is sum of some n natural numbers or consecutive n natural numbers, and if you write a specific equation for this series, it will be also of the form n square, and that is why the recurrence relation T of n equal to T of n minus 1 plus n has a complexity of big O of n square.